Yesterday we'll talk about CADSOL. I mentioned the basic ideas of how it works, and we also use this solver to try to obtain a numerical solution of a paired black hole. For that, we use Mathematica to obtain the equations, the boundary conditions, and to print everything in a Fortran file. And with that, we copy everything to a Fortran file so that we can run it. Something I didn't do yesterday was show how well the functions, the numerical functions, are compared to the numeric ones, or the analytic ones, right? And here we have results for the F1 function. So the lines, which basically this is a red line, there's a green line, there's a blue line, although it's a bit hard to see. These are the analytical functions or the analytical solution, and the plus symbols, the cross symbols, and the star symbols are the computed function. So red and the plus are for θ equal to 0, as you can see. The green and the cross symbol is to pi over 4, and this line here and the stars correspond to pi over 2. And as you can see, they're quite very well in agreement. There's no big difference. But to have a better idea, here I computed the absolute difference between the two. So the exact function minus the compute one, and just some ABS, some norm. And as you can see, most of the points are between 10 to the power minus 5 to minus 4. So you can see there is quite a well agreement between the two. But, yes?
So do you understand why there is a maximum for difference at some x?
Well, here, since it's close to the horizon, maybe.
The horizon is at 0.
Yes, it's at 0, but since this is, it's a scale of it doesn't, so in 0 is the horizon, and in 1 is at infinity. So most of the points are closest to the horizon. So this maximum, I don't know exactly the answer, but I will assume that since it's close to the horizon, maybe there is some something that increases a bit the difference close to the horizon. Maybe this could go away if we consider a grid with more points close to the horizon to have a better better result. I will assume that in principle that should decrease the difference.
Sure.
But now I'm going to talk about boson stars. So they already talk about boson stars, and also Alexandre also talk about it. But for the symmetric case, here I'm going to talk about the rotating case. These are horizontal self-gravitating solitonic-like scalars, scalar field solutions of the Einstein-Klein-Gordon action, as you can see. And we have a potential here, this V, that's for the case of mini boson stars, which is the ones that we're going to talk about. You only have the mass term. You can also add some other terms of higher order, for example, the self-interactions. But now, what are the differences from the Kerr problem? So here the idea is to do basically the same as we did for the Kerr problem, but there will be some difference. The first one should be obvious, since they are horizonless. The RH quantity that was the input parameter for the Kerr problem no longer is an input parameter here, since we always put that to 0. There's also a presence of a scalar field, so there will be a new Anzac function. So we have one more function to compute. And the third and last difference, or biggest difference, resides on the redefinition of this W function. Then you'll see that now our new Anzac is this one. Again, I use the red color to simplify or to say that those are Anzac functions. So here we have the F0, F1, F2, W, and phi Anzac functions. So now we have 5 instead of 4. And I also use the green color to indicate input parameters of the problem. So as you can see, now we have this phi function, which is a new untitled function of the problem that depends on r and theta. And we have two input parameters, which are the angular frequency of the scalar field, this omega, and this m is the azimuthal harmonic index. That can be 1 plus 2, plus or minus 1, plus or minus 2, and so on. Yes. Why do so? Nuno is asking about this redefinition of the W function. Well, it's not entirely necessary, but it's better for the numerics. Basically, that's the idea. If you didn't do this redefinition, this double function goes as 1 over r to the power of 3. Plus, in other words, it will go very fast to 0. And if you do this redefinition, it goes a bit more smooth. It goes as 1 over r squared. Or you can even do w over r squared, and you'll go on. Yeah, basically, it's better for numerics. But if you want to have a better understanding, maybe you can speak with Eugene. He knows a bit more than I do about this, so you can speak with him. So now, since we have a new metric, now we need to impose the boundary conditions. The boundary conditions are the same for curve, for the f1, f2, f0, and w, but now we have a new untitled function, which is this phi, and we need to impose the boundary conditions. So the asymptotic boundary condition is basically the same as for the other one. So as we approach infinite, the phi must go to 0 in order to have flatness at infinity. Then at the axis symmetry and regularity implies that the scalar field must be 0 at the poles. Again, we can do the same as we did for curve, and since there is an equatorial symmetry, and we can compute everything just in this region between 0 and pi over 2, yes. And we impose that on the equatorial plane, the derivative of phi in order to theta also must go to 0. Then finally, here it's not on the boundary is not on the event horizon, since there is none, but it will be at the origin. Since it's on the origin, we do not need to do the same radial transformation as we did before for the curve case. You just have to do the power expansion around the origin, and we'll find that it goes like this expression. So we can easily impose that the derivative of phi in order to r must be 0 at the origin. Then with this, you can go and find what are the equations of motion. In this case, it's a bit more complicated than for curve, since now we have the Einstein equations and the Klein-Gordon equation. So this box here is the Lambertian operator, and the energy moment tensor here is given by this expression. So in order to perform the numerical integration, it is useful to use dimensionless variables. As you can see in this energy moment tensor, there's this quantity, the mass of the scalar field. So it's better if we write everything in terms of this mass. So that's exactly what we do we did here. Then, with this, you can go to Mathematica. You can do exactly the same as we did yesterday. Have a Mathematica file to obtain the equation of motion. Then add another one for the boundary conditions, and to motivate why we chose those boundary conditions. And then with the third one, obtain do all the prints and all the four-term forms, so that you can copy everything for a four-term file, then to run it. In this problem, you had also a bigger problem, which is is related with the initial guess. For the curve problem, it was quite easy because you have the numerical result. But here you don't have any numerical result to start with. So one idea that you can do is take the spherical case of the Boson star, which can be obtained numerically using Alexander code, for example. And you can then that spherical solution corresponds to m equals 0, then you can basically use that and increase m solely. So you start with m equals 0, go to m equals 0.1, for example, then 0.2, 0.3, so on, until you reach 1. After that, since you have that one, you can use that to obtain the rest of the domain of existence. But here I'm more interested in showing you, I sent you a solution of a boson star, a rotating boson star, and I'm going to show you how to extract physical information for that solution. From all the files that I send you, how can you extract information from there? So we'll go again to our beloved Mathematica. So this is the, the extract data, if not mistaken. And well, in the beginning, I do the same, clear variables, nothing more. Then here we set the directory to the same as where the notebook is, together with the file, the directory where the files of the solution are. And here we can start to extract all the information that we want. For example, this res file from yesterday, we saw that this is a file where we put all the input parameters. Here we just need the angle frequency, which is in this case in the second column. Then we can extract the grids, associated to the r variable and the theta variable, and the number of points that each one has. Then you can start to extract all the exact functions. So here we have f1, f2, f0, phi, and w. Here I also have a part, so I have here this for the origin, or for the horizon for the case of black holes. Here it's not needed, but for the case of black holes you may need this. For example, if you want to compute the Hawking temperature, the horizon area, you will need information on the horizon, so you need this part here. Since we are talking about boson stars, you don't need that. Then this file is where the Ricci scalar, the Kretschmann scalar, and the two constraints equations are. So if I'm not mistaken, yeah, the first column is associated to the Ricci, the second and the third is the first and the second constraint equation, and the fourth is the Kretschmann scalar. Finally, you can also import the information about the energy momentum tensor. In this case, these three quantities. Now you can start to do some plots to see if all the functions are smooth, if everything goes well. So here are just some plots for f1, f2, f0, w, and phi. As you can see, everything is smooth. There's no divergences. You can do the same for the Ricci, the Kretschmann, and for the energy moment tensor, or for the components that we have. Then, after that, you can start to obtain the physical quantities. So here I have the part for the horizon, but you have the Hawking temperature, the horizon area, and these two quantities, which is associated to the length around the equator and around the poles, but this only works for black holes. But since we are working with boson stars, that doesn't make sense. That's why it's all comment. But I left it here, so if you someday obtain a black hole solution, you can use this to compute those. So for the mass, there are two ways to obtain the mass and the angular momentum of the boson star. The first one is from the asymptotic behavior. The asymptotic behavior of the two metric functions, the GTT and the GT phi, must go. The first one must go as -1 plus 2m over r, and the second one should go as -2j over r sine squared. So if you do asymptotic expansion of these equations, you will find that the f0 function has the mass there, the information of the mass, and the W function has the information for the angular momentum. So we only have to do a simple linearization here in 1 over r and here in 1 over r cube. So in relation to your question, Nuno, if you didn't put or define the W for W over r, this term will go as 1 over r cubed instead of square.
The reason is behavior at large, not at the we can
Okay.
discuss that afterwards.
Okay.
Yeah.
I thought it was more about the static behavior. Okay. Then with a simple linearization, you can obtain the mass and the angular momentum. And that's it. Exactly what we do here. For each value of the grid on theta, for each value of theta, we do the fit. We fit with 1 over r or 1 over x here, and over 1x squared, and we'll go get the 1 over x component. And we do the same for the double function for the angular momentum. And with that, you can just do an average for all the values of theta and obtain the total mass and the total angular momentum. With that, you can also compute the reduced angular momentum and the spin of the Boson star. The same can be done through the Komar integrals. The Komar integrals are defined as this expression. I will not explain a lot of what those are, but well, are some very known results. And if we expand these integrals, we will obtain these expressions. For the mass, we have this integral, and for the angular momentum, we have this. In blue are the quantities that we already have from the energy momentum tensor on the file. So the only thing that you have to do is extract those quantities for Mathematica and do this integration. So you can do the integration to obtain the mass and the angular momentum, and that is exactly what we have here. So here's just a table for all thetas, and here we have part of the expression. Here is where we'll go get the information from the file. And we can do this. This one is for the angular momentum, and this one is for the mass. You can do interpolation and integrate first in all thetas, and then do the same for all r's. So because we are integrating over all radial coordinate and all the angle coordinates. Doing this, we'll obtain the mass and the angular momentum, which in this case should be the same. For the case of a black hole, for example, a curved black hole is kilohair, this will not be exactly the same because we also have the mass associated on the horizon. Then, with this, after this, you can go and start to compute other things, such as the compactness. The compactness, Alexander already mentioned in his presentation for the spherical boson stars. This is, well, for the boson stars, you don't have a well-defined surface, but you can define one more or less in the following way. You start to compute the perimeter radius, which contains 90% of the mass, the total mass. This perimeter radius is just a radius for which the circumference around the equator has this perimeter. So in this case, this is quite easy to obtain. You just have to compute this formula. Then, with that radius, you compare it with the Schwarzschild radius for an object that has the 19% mass of that boson star. So basically, you only have to compute this ratio, and you have to define basically the inverse of the compactness. So to do this in Mathematica, first we compute the mass, the 90% of the total mass. Then we do interpolation of the mass function here in before. Instead of only obtaining the final value for the mass, what I did was a vector with all the masses computed for all the points on the radial coordinate. So if it is on the horizon, it should be 0. Then as you move along the radial coordinates, for each point, the mass will grow up until we go to infinity and should go to a value, a fixed value. So you can use this and interpolate that. So we can find where, for which radial coordinates, the mass is at we have 90% of the total mass. Having that radius, you can now compute the perimeter radius using the formula that I mentioned before. And finally, first we have to also interpolate the f2 function to compute what is that value. We can put the perimeter radius and then the inverse compactness. Now, for some Boson stars, it's possible that they can develop agar regions. These agar regions are regions on the space-time where this quantity d over t becomes positive. They already talked about this for the case of Kerr. And these regions are bounded by a agar surface when this d over dt, the norm of it, goes to 0. In our case, this is just basically the GTT part of the metric must go to 0. This defines the agar surface. As shown by Professor Herdeiro, this is the agar surface for a Kerr solution. So this sphere here is the event horizon, this outside is the agar surface. But for the case of Boson stars, it's a bit different. You have something like this. So the topology is a bit different. This has a toroidal topology. So here on the mathematical file, what I did was just a check to see if this particular Boson star has an agar sphere. So the first thing you do is define the GTT component. Then here I also do a plot just to see. So as you can see, GTT goes above 0. For example, on theta equal to pi over 2, you can see there is a region in which GTT goes above 0, so there is an agar region. Then here, what I do is just check if I check if there is such agar region and count how many points, how many zeros the GTT function has. And in this case, I only do for the equatorial plane, since I already know it has a toroidal topology. In principle, it should only have either 0, when you don't have any agar region, or 2, because we will cross 2 times the 0. And here is just to I interpolate the GTT function just to find to what value of R these the agar regions appear. Moving for the next part, you can also compute the light rings. Very simply, light rings are circular orbits of light around, in this case, the Boson star. And if the Boson star is compact enough, it can develop light rings. But not all Boson stars will develop. To do this, I have here some quick recipe that you can follow to obtain the light rings. So first, you start with the effect with the Lagrangian for geodesic motion of a massless test particle on the equatorial plane. So your Lagrangian will look something like this. Then you use the symmetries of the problem to rewrite the t dot and the phi dot. So here the dot is the derivative in order to the proper time. And you can write this in terms of the energy and the angular momentum of the particle, like this. Then you can use this result and put it again on the Lagrangian and obtain an equation for R dot squared. This will define potential. With this potential, since you want circular orbits, you have to impose that both the potential and its derivative, in order to R, in this case, must be equal to 0. The first equation will give you 2 equations for the impact perimeter here, and the plus and minus corresponds to and counter-rotating orbit, since this is this Boson star is rotating. And the second one, the derivative, together with this result, will give you the radial coordinates for which the light ring will be for both the co and the counter-rotating case. But in the end, what we have to do is basically find for each r does this equation go to 0. So the plus sign corresponds to co-rotating and the minus to counter-rotating. In the case of these Boson stars, there are no co-rotating light rings. You cannot find anything. So this will never be 0. But for the counter-rotating case, we will find, for some compact Boson stars, you can start finding some counter-rotating light rings. In terms of Mathematica code, here I do again just an interpolation. This is equal, I don't know why this is repeated, but yeah. This is just an interpolation for the f function and the double function. And we define that last equation that I mentioned. So as you can see, in this case, if we do the plot of this, this equation, you see that it's never cross zeros. It doesn't have any roots. So there is no co-rotating light rings. Sorry. Just to confirm, you can do a simple line of code just to verify that you never cross any zeros. Yes. No, it's a property of the Boson star. Even the most compact objects or rotating Boson stars do not develop. Yeah, that's why I obtain yes. Yeah.
Can you repeat the question? So we
Sorry. Alexander was asking if this property or this result that we did not obtain any co-rotating light rings, if it was just in this case or if it was for all cases.
Okay.
And what I'm answering is that for all the solutions that we obtain, which are a lot of them, but yeah, you can always go to even stronger gravity regimes. But at least for the ones that we obtain, none of them develop co-rotating light rings, only counter-rotating.
Thank you, Josh.
Go. That I have? No. To be honest with you, I don't have. Maybe are there? Yeah, maybe are there as one. To be honest, I don't have any intuition why, any intuition reason why that happens.
Well, I would say that it was not expected.
Okay.
But if you think about the curve, the light fields, the co-rotating light fields are always closer to the horizon. And the light fields appear in the toroidal region when they appear. And then you would expect the co-rotating light fields to be moving towards the most compact region. But if they would go inside, it's not as compact because it's toroidal, you see, so it's not stronger gravity. So I think maybe there is a nicer way to put it, but we haven't found the words, and it's an interesting challenge, I would say.
Thank you. So for the co-rotating case, we do the same. As you can see now, there are two zeros. So as you can see, we have two light rings, two counter-rotating light rings. This is also interesting, given the result that Pedro Cunha and Herdeiro and Eugene obtained, that for a Boson star, there will always be a pair of light rings if the Boson star can have light rings. So it's either 0 or either 2. And here we see that. Here again, we can just check to see if there is true. You only see 2 light rings. And here is just to find which is the radial coordinates of the light rings. And here is just to verify if they are stable or unstable. In this case, the outer light ring is unstable and the inner light ring is stable. Then, another thing you can do is study the energy conditions. These energy conditions exist to verify if the angle, the energy momentum tensor is at least at the level of classic physics, if it is viable, basically. So for any time-like vector field, we have the weak energy condition defined as this expression. Like basically it says that the energy density measured by any time-like observer must be non-negative. This, for the Boson star case, can be shown that it's always true, so there is no violation. But I want to show you at least one example, and so I chose to an observer, which is the so-called zero angle momentum observer. And for this type of observer, if you expand this equation, you obtain something like this. And as you can see, these two quantities are on that file about the energy momentum tensor. Then you can also study the strong energy condition, which is given by this expression. And in this case, this just means that matter must gravitate towards matter. And again, for the zero angle momentum observer, we obtain a very similar expression, which is this one. So in the Mathematica, you can study these equations, or these inequations in this case. So for the energy, weak energy condition, you can define it and you can plot it. So you can see here, it doesn't appear to be violated. All the lines go towards zero when you go to infinity, but none of them cross none of them go towards negative values. And this code here verifies that. Then, for the strong energy condition, you can do exactly the same. You can also do some plots, and again, you can see that it goes towards zero, but it doesn't appear to go below zero. And again, this small code just to verify that. In the end, you can print everything that you obtained so far. So, for example, the ADM mass, it's this value, and the mass obtained by the combined integrals, as you can see, it's similar. Not exactly the same, but it's quite very close. Then the angular momentum can be, as you can see, is basically the same, and the other quantities as well. Here we have the compactness. Since it's the inverse of compactness, and you expect that a boson star is less compact than a black hole, this value is always bigger than 1. Then here we see that the solution has two ecoregions, that it has no co-rotating light rings and has two counter-rotating light rings. And we also see that the weak energy condition and the strong energy condition are both not violated. So that's basically what I want to show you here. But now, since I didn't mention before, since I have still a bit of time, I can show you. This was only for one solution, but you want to have all the solutions in the domain of existence. But for that, since this method uses a Newton-Raphson method, or the solver uses a Newton-Raphson method, you have to always provide the initial guess. But this initial guess normally is just a challenge in the beginning, because as soon as you have the first solution, you can always use that one to obtain the next one. So for example, here we only have one input parameter, which was the omega, the small omega, which is the angular frequency of the scalar field. If you obtain the first solution, for example, the 0.9, then you can use that to obtain the 0.8, then the 0.7, then the 0.6. These are big jumps, but the idea is that. So what I do, just to show you the code itself, I use Blackfish, as you can see. I will not use my computer to, or I will not use my computer to do this type of calculations. And for this case, I can show you just the V14 file that I showed yesterday for the Kerr case. Here is for the black hole, sorry, the boson stars. In this case, particularly this case, is the action boson star, which is another problem. But here, instead of just defining the parameters by hand, like here, I use a file called parameters, where I put there the initial or the parameters of the problem. So here is the angular frequency of the scalar field. And then, I also use a bash file to basically do a for cycle for all the angular frequencies values. We start with 1 that I already have, then in this case decrease by this step until we reach some value. With this value, I just put within the parameters file, and then with the Fortran file, the v1.4.4 file, I will just go there, grab the values, and run everything. So this way, I just have to run this batch file, and we'll always get start with the initial guess, obtain the next one, and then with that obtain the next one, and with that obtain the next, and so forth and so forth. This, unfortunately, will give you, for example, the first branch. If you want to obtain the second branch, the lower branch in the others, I don't have a code as good as Alexandro had in this presentation. But to obtain the second branch, the way that we do is basically go to the end of the first branch, try to obtain a solution which is outside of the branch that the solve will not converge, and then use that as initial guess for the second one branch. This is an idea. It's not very, very precise. Sometimes it works, sometimes it doesn't. But well, it's an idea. A different idea is try to use a quantity input parameter, which is a quantity that doesn't go back and forth like the first branch, second branch. Something like increases always. If you use that, you can do something like Alexandre did and just vary that quantity, and you obtain all the equations, all the solutions. Sorry. But yeah, for now I only have this, unfortunately. So yeah. I have still a bit of time, but just to also talk about this project that I have with Philippe, we are trying to obtain these solutions with deep learning. It's a complicated problem. Maybe we didn't press that idea in the beginning to try to use deep learning, but at least for the PDEs, nonlinear PDEs that we show, it's possible to obtain a solution, although the one that we obtained, it's not the right one, but it's possible. There are some papers that already did that. But here it's even harder because it's even nonlinear, and we have several functions. You don't have only one function to obtain. For example, for the car case, we have 4, and we have 2 parameters to change. In this case, we have 5 functions and have 1 parameter to change. So it's a bit trickier. Maybe you can do it, maybe you cannot. Let's see. This is it's only an idea that we want to try to implement. If it works, nice. It will be a very nice result. If not, well, it's life basically. But yeah, that's what I want to show you and talk about. Yeah, I have good faith. I want that to work, but yeah. I want to be optimistic, but yeah, sometimes you have to have your foot on the ground. Yeah. Yeah. It has something like. It always has something there. Well, for me, if this doesn't work, at least I understand a bit more about deep learning and how to program deep learning. So for me, it's always a win-win situation. But yeah. So then I can put on my resume. So yeah.
Okay, so now there is a question about who sees the cup half empty or half full. But I think this basically wraps up George's presentation. And also, there are any questions online? There are no questions online so far, and here in the room there were a few questions already. I don't know if there is any more comments. And if not, let's thank George. And now we will have a little yes, but let me just see who is next.
It's you. It's Nico.